For this next module, we're going to be looking at bonding and molecular structure, orbital hybridization, and molecular orbitals. We have two major topics in this section, and that's valence bond theory and molecular orbital theory. And these two things have some things in common, but there are different approaches at looking at bonding in molecules. So first, we're going to take a look at valence bond theory. Let me see if I can zoom out just a little bit. All right, so in valence bond theory, we want to understand how sigma and pi bonds arise through orbital overlap. And we want to be able to identify the hybrid orbitals used to match the electron pair geometry of the central atom. So this symbol here is sigma, and this symbol here is pi. I'm sure you're familiar with the pi symbol. So right now we're talking about valence bond theory. So let's look at the orbital overlap model of bonding. So here's a hydrogen molecule in H2. Each hydrogen presumably has a 1s electron that it brings to the game. And so here are the two 1s orbitals with an electron each. Now, when these two approach one another, the orbitals overlap. And there's actually a very good diagram in your book that shows what happens to the energy when these two orbitals meet. And so let's take a look at that energy diagram. You can look in the book and see it, but I'm just going to draw it very quickly here. So this is going to be distance between the nuclei. And when I put this arrow like this, it's pointing to where you have the greater distance. And the opposite direction would be the smaller distance. And this is going to be the energy. And it's really potential energy that we're looking at. And here, this would be more potential energy, and this would be less potential energy. So I'm going to put a little arrow going up like this. Now, when something has more potential energy, it's actually less stable. And when it has when it has less potential energy, it's more stable. So really, this is a stability plot where the lower it is, the more stable the plot is. Now, the energy interaction, when the nuclei distance is very small, it's very unstable because the nuclei are repelling one another. And as those nuclei get farther apart, it actually becomes more stable. And what happens here on the other end is if they are infinitely distant apart, the energy between the two atoms is essentially zero. So this means that there is no attractive interaction between the two atoms, and there's no repulsive interaction between the two atoms. So the two atoms are very far apart. And here, the two atoms are essentially right on top of one another. So here, they're too close together. Here, they're too far apart. Very close together, very unstable. Very far apart, no energy relationship between the two. Now, as they start getting closer together, there is a force of attraction that's happening. The electrons of one atom are attracting the nucleus of the other, and the same goes for the other atom. The electrons of that atom are attracting the nucleus of the other. So here, you have essentially no energy, and as they get closer and closer together, eventually you have these attractive forces. And these attractive forces are stabilizing. Now, when you have the maximum of the attractive forces and a minimum of these repulsive forces, you reach what we often call an energy well, because it looks sort of like a well if you think about a hole in the ground. And this distance right here apart is the bond length. Now this diagram looks the same for any two orbitals that are bonding. You will have this repulsive force where the nuclei are getting too close together. You'll have essentially no energy when they're too far apart from one another. And then you will have this energy well where these attractive forces of the electrons for one atom, for the nucleus of the other, stabilize the bond formation. And the difference between each of the drawings for each of the orbital overlap, and so here for the orbital overlap, we're looking at this. So there's the orbital overlap right there. What we're looking at is let's see, where did I leave off on? Well, the electrons of one atom are attracted to the nucleus of the other. So here in this energy well, you've got the maximum of attractive forces, and it's very stable. So again, this diagram is going to look the same for any two orbitals that overlap, but this bond length is going to change and the stability is going to change. But this is the general look at it. So you could have a 2p and a 2p overlap. What I've drawn here is like a 1s and a 1s. But if you had a 2p and a 2p overlap, here's a 2p and here's a 2p. These guys are infinitely far apart, so there's no interaction. And here they're starting to get close enough to one another, so you have some interaction. And here you have some orbital overlap. So that's the idea of orbital overlap. And then of course here, they're too close together so that they actually are really repelling one another because the nuclei are too close together. So here, this would be a 2p and a 2p. And here's the nucleus, and here's the nucleus there and there. So this is the energy level diagram. Energy diagram for orbital overlap. And the only thing I really haven't shown you here is that in this overlap, if I draw it a little larger over here, you're going to have these electrons that are being shared. And so here, each one of these has one electron. Naturally, when they come together, one of the electrons has to flip so that you have a spin up and a spin down. And this is often drawn, so this is equivalent to this, where the orbital overlap is right here between the two nuclei. Okay, so that's the orbital overlap diagram. So that'll help you to understand what's going on here when you have two orbitals. This is a 1s and a 1s. They overlap, and you have a bonding orbital, or a bonding two orbitals. Now, this is called an atomic orbital because it's on one atom. Here, you have a hydrogen and fluorine bonding, and here's the hydrogen, the 1s. The fluorine is a 1s2, 2s2, and a 2p5. So here, you've got this one orbital here. We'll call that a 2px, okay? So here, that's on the x-axis, and that is going to overlap with this 1s from the hydrogen. And here's the overlap right here where you form a bond. You could also have an overlap between a fluorine and a fluorine where the 2p and the 2p, so this is a 2px and this is a 2px, and here you have this overlap. Now, all of these bonds here are called sigma bonds. And they're called sigma bonds because the overlap occurs directly between the two nuclei. Directly between the two nuclei. So what would be not directly between the two nuclei? Well, we can take a look at that in a bit. But first, let's look at the application of this idea here to a simple overlap model of bonding in H2O. So in H2O, you have two hydrogens, each with a 1s and one electron. With oxygen, you have a 1s2, 2s2, 2p4. And remember, with Hund's rule, when you put electrons in here, you put them together singly before you pair them. So we're going to end up with two of these 2p orbitals that have one electron each. And these p orbitals are perpendicular to one another. Okay, so you have three of these. And what I've drawn here is, we'll pretend that this one is a 2p x and a 2py, and this will be the 2pz. The 2pz is the one that goes in and out of the plane of the paper. So here, this would be the 2py, this would be the 2px, and those are those two 2p orbitals, and you can see that they are orthogonal or perpendicular to one another. And when the hydrogen bonds with this 2p orbital with one electron in it, you get this orbital overlap here, and there's your bond. And when the other hydrogen bonds to the other p orbital, you get this overlap here, and there is the bond. So orbital overlap. Now there's a bit of a problem with this model as it stands, and that's that we expect a 90-degree bond angle because the p orbitals are 90 degrees to one another. We actually get a bond angle here in H2O of 104.5, which is clear to 109 which is closer, not clear, closer to 109.5 than it is to 90 degrees. So this seems like in the previous chapter, we were looking at, let's see, we were looking at an electron pair geometry of tetrahedral. And then when you look at the overall geometry for the molecular, we'd call it bent 109.5. It's a little smaller, but that's okay. It's pretty close to 109.5. So what's going on here? Because this orbital overlap model doesn't seem to be working. This valence bond overlap doesn't work too well. And let's explain that word valence. We're talking about valence orbitals that are overlap. This is the valence orbital for the hydrogen. These are all the valence orbitals for the oxygen, so the valence orbitals are overlapping. Well, there's a solution to this. So if we need to, what we do is we say the orbitals can remix and then separate and make new orbitals. Those orbitals are called hybrid orbitals. And what will happen is that in this case, since you have four valence orbitals, they can overlap, they can mix and then separate and make four equal orbitals. So notice when I draw the energy level diagram or the electron configuration for fluorine as an energy level, the 1s is more stable than the 2s, the 2s is more stable than the 2p. There are three 2p orbitals. So what happens is these four orbitals in the outer shell, they mix together and then they become a nice even mix, and then you chop it into four pieces, and those four pieces become four orbitals. Now, those four orbitals are an even mixture of these four orbitals that make them. So that means they're going to be 1 part s and 3 parts p, because we're mixing 1 of the s orbitals and 3 of the p orbitals. So that's why they're named sp3, because they're 1 part s and 3 parts 3. Now, the reason this is called a 2 sp3 is because we're mixing 2 s orbitals and 2 p orbitals. Now, if you mix these orbitals together and you come out with the hybrid orbitals, each of the hybrid orbitals has the same energy, and it'll be somewhere between the 2s and the 2p energy because it's got partial s character and partial p character. We'd expect these orbitals to be closer to the p level because it's 3 parts p than to the s level. So now if we look at Hund's rule and we put the electrons in here, you've got these two here, 1, 2, 3, 4, 5, 6. So we've got, and remember, we're looking just at we're looking at all the electrons, not just the valence electrons, but this is what this would look like for fluorine. Okay, this is just fluorine, not hydrogen. So the next thing you have to undertake is this, is if you have 4 hybrid orbitals, how will they orient themselves around a central atom? And this is where it matches the electron pair geometry. 4 orbitals will orient themselves in a tetrahedral arrangement around an atom. So here, each of these is an sp3 hybrid orbital, 1, 2, 3, 4. And when we look at this fluorine, notice we're not drawing this 1s here. We're just drawing these 4. There's 2 electrons in one, 2 electrons in another, 1 electron in one, and 1 electron in one. It's this orbital here with 1 electron in it that can overlap with a 1s from the hydrogen. So this is our hydrogen. And here, this one can overlap with the 1s from the hydrogen. So when they overlap, this is what you're going to get. And you get the 109.5. So this is sort of like a combination of VSEPR and hybridization. Only when we talked about VSEPR, we never talked about, well, that there are orbitals overlapping. We just said that there's regions of electrons and they repel one another. We didn't say what those regions were. We just said, hey, they repel one another. Okay, so here we're given kind of a credence, if you will, to what those regions are. They're hybrid orbitals. So let's look at the different types of orbital hybridization. Before I move on, I do want to make sure that you understand that these are called hybrid orbitals. Okay, so what we're doing is we're hybridizing these second shell orbitals. They don't have to be second shell. They could be third shell. They could be fourth shell. They could be fifth shell, whatever. But they're N, S, and NP orbitals. So they're both from the same shell. So here we could hybridize one of the NS and one of the NP. And when you hybridize two orbitals, you're going to get two hybrid orbitals. And here, since it's one part S and one part P, we call those SP orbitals. So here we'd have two SP hybrid orbitals, hybrid, and you have two p orbitals that have not been hybridized. So we call them unhybridized. So notice we start with 4 of these atomic orbitals, and we still end up with 4 atomic orbitals. Only 2 of them are hybridized. So here's the SP and the SP, because what we do is we think to ourselves, well, how will these hybrid orbitals be arranged around the central atom? And the answer is we use that electron pair geometry idea where they will be as far apart from one another as is possible. So they'll be linear here. We have linear hybrids. So what about these P's? What happens to them? Well, they're still centered on the atom. So remember, that's the center of the atom, the nucleus. So one p orbital will be going straight up and down, and one p orbital will be going in and out of the plane of the board. So this is what it looks like. And this can be a confusing drawing, so you need to read this material very carefully. This SP is an orbital. This SP is an orbital. They're hybrid orbitals. These 2 lobes are one p orbital, and these 2 lobes are another p orbital. So they look kind of the same, but you have to understand that they're different. And so that's why I have labels in there. So we have 4 orbitals here. 2 are hybridized, 2 are not. You could hybridize 3 of these. So 1, 2, 3. Notice whenever we hybridize, we always hybridize one of the most stable orbitals with the least stable. So here we're going to hybridize 1 S and 2 P's. So naturally, if it's 1 part S and 2 part P, we're going to call them sp2 hybrid orbitals. And if we're going to hybridize 3 of them, we get 3 hybrid orbitals. So what happens to the third p orbital that's not hybridized? Well, it remains unhybridized. So we have 3 hybrid orbitals and 1 unhybridized. Now, in this case, for me to draw it, it makes more sense to take the sp2 hybrid orbitals and draw them like a flat triangle. But instead of drawing it like a flat triangle like this, I draw it on its edge. And here you can see that the leftover p orbital, we shove that in there where it's going to fit the best. In this case, if I draw this flat triangle like this, the p orbital fits best going straight up and down like that. And so that's what I've drawn here. So the hybrid orbitals are trigonal planar. And each of these hybrid orbitals can bond, but so can that p orbital. It can bond. Okay, so what happens when you have 4 pair? You're going to get sp3 hybrid. And so I'm going to back it up just a bit so that you understand what this 4 pair means. So if we go back to here, notice if we have 2 pair, it's sp hybridized, 1, 2. If you have 3 pair, like in BH3, 1, 2, 3, it's spp hybridized, 1, 2, 3. We don't say spp, we say sp2. And here, if we have 4 pair, like with this molecule, it's going to be spp hybridized, so sp3. And the arrangement of these 4 hybrid orbitals, all of equal energy, or degenerate, as we would say, equal energy, they're going to arrange themselves tetrahedrally. Now, the book goes into this, but not into too much detail, but I went into it a little more in detail. We also have orbital hybridization where you can use an S, a P, a 3, and a D. Remember, for the Lewis structures, we did have some of those atoms that can have 5 regions. 1, 2, 3, 4, 5. So how do these work? You're going to have S, P, P, P. And when you've used 4 orbitals and you've used an S and 3 Ps, you then have to start to use a D. So I'm going to use this, and this is my D. All right, so you've got 1 S, 3 Ps, and 1 D. So they're called sp3d hybrid orbitals. And so here, this can only occur in those elements that have electrons in the D block. So we're talking the 3rd period or 4th period or 5th period. So some of those elements might have 5 bonds or might have 6 bonds, or it might, as we say, it might have 5 pairs. So here's something that has 5 pair. So we hybridize an S, a P, a P, a P, and a D. So 4 of the Ds remain unhybridized, and they don't really participate in bonding. And 1 of the Ds hybridizes with 1 of the S's and 3 of the P's, so we call these sp3d. So how do 5 orbitals arrange themselves around a central atom to minimize repulsion? In a trigonal bipyramidal. So these are trigonal bipyramidal hybrid orbitals. And there's one more type of orbital hybridization that you should know about, and that is the time when you have 6 pair around your central atom. So for 6 pair, you're going to need an S, 3 Ps, an S, I'll put my hand here, an S, 3 Ps, and 2 Ds. S, P, 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 D, D. So what do we call that? sp3d2. So what we're doing is we're hybridizing this S, these 3 Ps, and 2 Ds to get 6 hybrid orbitals because we're hybridizing 6 of these. So if we hybridize 6 of these, 1, 2, 3, 4, 5, 6, what do we have left over? 2d orbitals that aren't hybridized. Actually, 1, 2, 3, 4, 5, 6. I need a 3rd one there. Okay, so we're hybridizing 1, 2, 3, 4, 5, 6 with 3 left over unhybridized. And remember, these unhybridized D do not participate in bonding as far as we care. So here you have these 6 orbitals, and how will these 6 orbitals arrange themselves around the nucleus of an atom? Octahedral. So you want to be aware of those different types of hybridization. You want to be able to identify them, and you also want to be able to draw them. Let's look at the summary of hybridization. And this is how we figure out the hybridization of a central atom. If it has 2 pair, 2 electron pair, it's sp1, 2. And there's 2 hybrid orbitals. If there's 3 pair, there's 3 hybrid orbitals, and each of them is sp2 hybridized. So sp2 is spp. Notice that the number of orbitals I draw here equals the number of pairs. We just don't write them this way because this is a little shorter. It's not really any shorter here because that's what, 3 letters and 3 letters. But here it is shorter. You got 4 letters and you got 3. So if you have 4 pair, it's sp3 hybridized. If you have 5 pair, it's sp3d hybridized. 6 pair is sp3d2 hybridized. And with 2 pair, it's linear, 3 pair trigonal planar, 4 pair tetrahedral, 5 pair trigonal bipyramidal, and 6 pair octahedral, just like with Vesper. Okay, so let's look at the valence bond description of bonding in methanol. Okay, so here for methanol, the molecule is CH3OH, so we have to draw the Lewis structure to figure out what's going on first. So we know that the carbon is going to be a central atom. The oxygen is probably also going to be a central atom. And the H3 means that you have 3 hydrogens on this carbon. So it's going to look like this. And you're going to have a hydrogen on the oxygen, clearly because the hydrogen is drawn next to the oxygen. And you're going to have lone pairs on the oxygen, so you have octets all around. And just to make sure, we're going to count these 2, 4, 6, 8, 10, 12, 14. And with 1 carbon, you get 4. With 4 hydrogens, you're going to get 4 valence electrons. And with the oxygen, you're going to get 6. When you add these all up together, you get 14 electrons. So you get 14 electrons for this formula, and we have 14 here. We've got octets all around where they should be, and we've got the duets on the hydrogen, so they can, they think they're like helium. So here's the nice Lewis structure. So let's identify hybridization on each of these. So how many pair are on that carbon? 4 pair. So what's the hybridization going to be? We have to hybridize 4 orbitals, an S, a P, a P, and a P. And when you put that all together, we don't say SPPP, you say SP3. So we have 4 SP3 hybrid orbitals on that carbon. What's going on with this oxygen? Well, we also have 4 pair. Remember, just like for Vesper, a pair can be a double bond, it can be a triple bond, it can be a single bond, it can be a lone pair. They each count as a pair. So, that weird definition of pair. So this oxygen also has 4 pair, so it's going to be also sp3 hybridized. So how do we draw this? Well, we want to draw this carbon so it looks like it's tetrahedral. So I'm going to go ahead and do that like this. And I'm going to put these hydrogens in place. So I'm going to put 1 hydrogen here, 1 here, 1 here, and I'm going to connect this bond to my oxygen. Now I want to draw this so it also looks like a tetrahedral. Now, when I do these things, I like to kind of do a zigzag thing. So you see I've got this straight line here, and a straight line here. So I call that a zigzag. So here, I'm going to bond my hydrogen here. So how do I make this thing look like it's tetrahedral? Well, normally what I would do is this. And you can see that does look like it's tetrahedral, just kind of rotated a bit. Now, I don't want to do this here for this oxygen because what goes here and here are lone pairs. I don't want to have this because this looks like a bond to a lone pair, and that's goofy looking. So here is the bonding that's going on here. And if you wanted to describe it, you'd say this is sp3 hybridized. It's tetrahedral. Tetrahedral hybrids. You would say it's a tetrahedral molecular geometry. And the angles are about 109.5 degrees. What would you say about this oxygen? You'd say that it's sp3 hybridized. And there are 4 orbitals here. 1 there for that lone pair, 1 for that lone pair, 1 for this bond, and 1 for this bond. And you would say that we have tetrahedral hybridals. Did I say hybridals? I think I did. Tetrahedral hybrid orbitals. Okay. And that would be a bent molecular geometry. And what do we have here for these hydrogens? Are they hybridized? There's no need to. They're just 1s orbitals. Besides, they only have 1 orbital, and you can't hybridize 1 orbital with another orbital because there are no other orbitals. Okay, so we could say that each hydrogen is a 1s unhybridized orbital. So it's that easy. Count how many pairs. From the pairs, you get the hybridization, and you go from there. Okay. All right. Let's take a look at another one here. Well, this is actually, this isn't the explanation. This is a problem, if you will, a conundrum. a question. So this is evidence that you can look up. And here, how do I want to describe this? Actually, this slide is out of order. I need to get a different slide up here. Let me find that. Okay, I must have dumped that slide by accident. So I'm going to have to draw it for you as I go. Unless I can find it. Nope. Okay, I want to put that right there. And let me show you something with these guys right here. So we have three molecules that I want to look at. One of the molecules has this formula, HCl, and we'll call it 2, CCClH2. This is called 1,2-dichloroethane. And if you draw the Lewis structure, it looks like this. 2 carbons bonded to one another, 2 hydrogens on each carbon, and 1 chlorine on each. And then if I draw on the dots here, I've got a great Lewis structure. So this is the Lewis structure of 1,2-dichloroethane. Now it turns out that this guy has a dipole. The dipole moment is 1.6 dBi. So that means when you put this in an electric field, it shows a molecular polarity. Now, the way I've drawn the Lewis structure, you would say, hey, it's nonpolar. But remember, you don't get molecular polarity from the Lewis structure. You get the molecular polarity from the molecular geometry. So here, if we apply molecular geometry to each of these, we could say, well, that's sp3 hybridized. And this one is also sp3 hybridized. And so if we draw it, it looks like this. So here's one hydrogen. And here is, actually, I'm going to make that one a chlorine, and you'll see why in a moment. I'm going to make this a hydrogen and this a hydrogen. And since this has a dipole moment, I want to draw this so it looks like it's got both of the most electronegative atoms on one side. Now, what are the most electronegative atoms in this? They're chlorine. So I'm actually going to redraw this a little bit differently. I'm going to draw it like this. So here, you can see that each of these is sp3 hybridized, so they have that tetrahedral geometry. And I've drawn both of the chlorines on the same side so that this is a dipole. Now, I could have drawn this another way. I could have drawn it like this. Bear with me here. So without thinking about it, I could have drawn it this way, and this is nonpolar because the two chlorines aren't on one side of the molecule. So if this does have a dipole moment of 1.6 dBi, that means when I put this into an electric field, it adopts this formation. Or it could be that this is the only formation that it has, right? And this doesn't exist. However, if you have two different molecules like this, where one's polar and one's nonpolar, you should be able to, if they're a liquid, you just put them into a container and they separate from one another. Because remember, polar molecules like to stick together and they exclude nonpolar molecules. So if I indeed have both of these, I should be able to separate them because they have different physical properties. However, this is not separable. So in fact, both these molecules are the same. And this is why we know that these things can rotate around single bonds. So it turns out that when you put this into an electric field, what happens is this thing makes a dipole so it can line up with the electric field. If you don't have the electric field, it can rotate. So this thing actually spins like a top. The only time it doesn't spin is when you drop it to absolute zero. So this is one molecule called 1,2-dichloroethane, and here's the formula. Now, on the other hand, we have other molecules, and other molecules are ones that are called 1,2-dichloroethylene. So the name sounds a lot like 1,2-dichloroethane, only this is called 1,2-dichloroethylene. Has another name, it's called 1,2-dichloroethane. And that sounds even, or excuse me, ethene, which sounds even closer to ethane. So I'm going to use my little white out there and get rid of that thing that looks like a smudge and make sure you know that's an E. So remember, the molecule we just looked at was 1,2-dichloroethane. And the Lewis structure looks like this. Well, here we have this 1,2-dichloroethene. Now, the interesting thing about this is actually, if you have this molecule, it's actually separable by physical means. So what does that mean if we can separate it by physical means and into two separate liquids? So how is that possible that we can separate these? Well, it's separable because it's actually two different molecules. So these are two different molecules because they have different sets of physical properties. They have different sets of physical properties. We know that because they don't mix. Okay, so what's going on here? Well, it turns out that if you separate them and you check and see if they have a dipole, one of them has no dipole moment, as they call it. So that would be 0 dibye. And the other one has a permanent dipole moment of 1.9 dibye. So the other one I think was 1.7. This one has a bigger dipole moment. And what's going on here? How can you have a molecule like this that has no dipole and then the same formula, it does have a dipole. Now the formula for this molecule is HCl carbon and it has a double bond. That's what the ene means, a double bond. So here's the formula. So how could we draw this molecule two different ways where presumably one of them does not have a dipole and the other does? And here we go. The Lewis structure looks like this. And I'm going to put the H there, the H there, the Cl there, and the Cl there. So there's your Lewis structure. How can we draw this two ways where you have a permanent dipole in one and no dipole in the other? Now here, how many pairs on that carbon? 1, 2, 3. 3 pair means it's sp2 hybridized. S, 1 pair, P, 2 pair, 3 pair. So it's sp2 hybridized. And how do sp2 hybridized orbitals arrange themselves? like that. So here, I'm going to draw these so that they're trigonal planar, if you will. And what I'm going to do here is I'm going to draw them like this. So here's the one with no dipole moment. And tell me after I draw this if you first of all agree that these are sp2 hybridized and trigonal planar. And then also tell me if you believe that it looks like it has no dipole moment. So the two chlorines are not on one side of the molecule, so it's nonpolar. Now, here's how you can draw the other one. You take the two chlorines, instead of having them be on opposite sides like this, you can have them both be on one side like that. So this definitely does have a dipole, and so that's why this has a 1.9 dipole moment. However, the only reason you should be able to separate these two is that here you cannot have any rotation around the double bond. So what keeps this from rotating, but you can have a rotation around a single bond? What's going on here? Well, it turns out we can use valence bond theory to explain why these things don't rotate. So let's take a look at bonding in these guys. And now I can get rid of these extra papers here. We can go back to here. So you've just seen kind of the problem that's going on here. So these are the molecules again. We've got 1,2-dichloroethylene, also called 1,2-dichloroethene. You've got one molecule that's polar, no rotation around this double bond, and you've got the other one that's nonpolar, and again, no rotation around that double bond. This, by the way, is called cis, and I think of that as cis same side, trans for like transcontinental opposite sides. And you got this 1,2-dichloroethane where you do have free rotation about this, and these aren't separable because it can rotate. Okay, so what's our explanation for how this works? Well, let's take a look here. The solution is pi bonding. So let's take a look at pi bonding. Now, before we get to pi bonding, I want us to revisit that sp2 hybridization. So I'm going to dig up my old sp2 hybridization here. And here it is. So here's the old sp2 hybridization. We have 3 sp2 hybrid orbitals and 1 unhybridized p. So this is what each of these looks like. Each of these carbons look like. So here I'm showing the 3 that are trigonal planar. And the deal here is that this guy bonds to a chlorine, this guy bonds to a hydrogen, the hybrid orbital bonds to the other carbon, and this hybrid orbital bonds to the other carbon, this hybrid orbital bonds to a chlorine, and this one bonds to a hydrogen. So remember, there's these p orbitals that are going straight up and down right here that I haven't drawn, but I've drawn them over here. So when you have these two p orbitals that are perpendicular, or not perpendicular, sorry, parallel to one another, they can overlap. And this is how we draw the overlap. So if I want to draw this in totality, it would get pretty complicated looking, but we're going to go for it anyways. So let me show you what's going on for that molecule. So I'm going to draw it 2 ways so that you can see you've got the cis and the trans. All right. So remember, we're drawing this molecule here, HCl, C, double bond C, ClH, 2 ways, showing the hybrid orbitals and showing pi bonding and sigma bonding. Remember, the sigma bond is when the electrons are directly between the 2 atoms. So here's one of the carbons. Here's the other carbon, and they're sp3 hybridized. So here's one of the sigma bonds. This is I think I said sp3. I should have said sp2 hybridized. Here's another sp2 hybrid orbital. Here's another sp2 hybrid orbital. And here's an sp2 hybrid orbital. And here's an sp2 hybrid orbital. Here's your hydrogen bonding to that. And here's your chlorine bonding to this. And I'm going to do the same over here. See if I can do this correctly. So here's a chlorine, and here's a hydrogen. And then here's one of your p orbitals overlapping with the other p orbital. So I need to get rid of the sigma here, and I put it right there. And this is a pi bond. Okay, so this is an overlap right here. So this is a sigma bond, this is a sigma, this is a sigma, this is a sigma. And this is what all the orbitals look like when you show them and how they're overlapping. And we can even put electrons in here, but it's kind of hard because of the size of the drawing. Okay, so what does this look like if I don't show the hybrid orbitals, but I just show the bonds? Let me straighten this up just a little bit. Okay, so here's what it looks like. Carbon bonded to carbon. So there's one of the bonds. Here, this chlorine is coming out of the plane of the paper. This hydrogen is going back. And here I could do this. And then how do I draw the pi bond? Well, just like that. Okay, because when we draw these without showing the orbitals, we don't really see that this is going to be a pi bond. So here we've got a sigma bond. Here we've got a sigma bond where the bond is directly between the two atoms. This is a sigma bond. This is a sigma bond. And here you've got a sigma bond, but you also have a pi bond. And here you can't see that it's a pi bond. You have to understand that there's only one bond between the two carbon atoms that's directly where the electrons are directly between the atoms. The other bond is above and below the plane of the paper, or the sigma bond. So this is the one that we would call cis. We're on the same side. So let's draw the other one where you have the trans and it's nonpolar. So there we go. So I'm drawing this side the same as that side, but on this side, I'm going to put the hydrogen coming forward and the chlorine going back. So here, this is the cis and this is the trans. And you could try to draw this similar structure here. It's kind of tough to draw, but this is the explanation for why there's no rotation, is because here when you have that pi bond, the overlap of two parallel p orbitals, if you rotate, you break that bond, and the bond is strong enough to keep it from rotating. All righty. So let's take a look at that in the book, because the book does a heck of a lot of a better drawing than I can do. So here, we'll take a look at the drawing that they have in the book for this. And this is it, right here. So here, this shows the three sp2 hybrid orbitals and the three sp2 hybrid orbitals here. And here what they've done is they've drawn the molecule so it's flat, and I drew it more like it was this. And here are the two p orbitals overlapping, and here's all of it put together. Clearly a better job than what I've done. So that's what's going on with this molecule. And you want to read more about this and see what's happening with triple bonds, because it's a hoot to try and draw. I wouldn't ask you to try and draw something like this on a test, but I might ask you to explain what's going on with the bonding. And so for this, what's happening is you have two p orbitals overlapping like this, but then you also have two p orbitals that are overlapping like this, where the p orbitals are perpendicular to one another like this. So these two are parallel. Actually, I should use two pens that are the same. These two are parallel, and these two are parallel. I don't know if you can see that. Actually, if I hold it like this, you can kind of see what's going on. So these two can form a pi bond. And if I drop those, these two can form a pi bond. Okay, so it's pretty complicated looking. Let's try some problems. Recognizing hybridization. So identify the hybridization in each underlying atom in the following compounds and ions. So right now they're just asking you not to draw anything, but just to recognize the hybridization. So let's look at SF3. SF3 plus. Sulfur has 6 valence electrons. Each fluorine has 7. And because of the charge, you actually have to subtract an electron. Remember, to make it positively charged, you have to take away an electron. So this is 21, then 20, plus 6 is 26 electrons. So for SF3, we're going to put sulfur in the middle, and we're going to put each fluorine around the sulfur. We're going to put lone pairs on each fluorine. And we've used 24 electrons, so we had to put 2 more on the sulfur. All right, so I'm going to scoot this a little more over. So here we realize there are 4 pair. So that's going to be sp3 hybridized, 4 pair, sp-p-p, sp3 hybridized. Now, sp3 hybridized is going to be tetrahedral. So for this molecule here, we want to draw a sulfur with 4 hybrid orbitals. One of those hybrid orbitals, I'm going to make it so that the lone pair is in it. And actually what I'm going to do is I'm going to draw the 4 hybrid orbitals. So here they are. And here for this hybrid orbital, I'm going to put 2 electrons in there. That's those 2 here. For this one, I'm going to put a fluorine plus the lone pairs around the fluorine. And this is the wedge. And here, this is the dash. And this is a straight line. So they didn't ask for all of this, but I went ahead and gave it to you. So the idea here is that it's sp3 hybridized. Why? Because of 4 pair. So how about this one? There's a nice little description in the book of this SO4 2-. The book tells you that there's really 2 Lewis structures you could draw for that. And the book prefers this one. And they prefer this one based on a theoretical study. So each atom has an octet, and that's theoretically more stable than what I prefer, which is this. Here, the sulfur has 6 bonds, and there are resonance structures. Okay. And the reason I prefer this one is that when you look at the formal charges, you get 2 negative 1s and 3 zeros. So this is a negative 1. This is a negative 1. This is a 0, 0, and a 0. When you draw it this way, you get a negative 1, a negative 1, a negative 1, and a negative 1, and then a positive 2. So here you have an unequal charge distribution. Here you have a more equal charge distribution. So I prefer this one over this one. And we're going to go with this one. But regardless of which one you go with, how many pair do each have? This has 4 pair. How many pair does this have? This has 4 pair. So with the 4 pair hybridization, what is the hybridization? 1s, a p, and a p. 1, 2, 3, 4. 4 pair. 1, 2, 3, 4. So we don't write SPPP, we write SP3. So even if you go with this structure instead of this one, it's SP3 hybridized. And how would you draw this? It would look like this. And what is the geometry? Tetrahedral. with angles of 109.5 degrees. Okay, what about this last one? This last one is more interesting because we've got a few things going on. So we've got this CH3, which we should understand now, looks like this. And then you've got a boron. And then you've got two of these OHs. So we're going to do this, OH, OH. And then we're going to put in lone pairs on each oxygen. Okay, and if you want to know if this is the correct number of electrons, we can always count them. How many for a carbon? 4. How many for 3 hydrogens? 3. How many for a boron? Let's see, 3. No, boron. Let's look at the periodic table. What do I do with my book? Boron's going to have 3 valence electrons, group 3A. Okay, how many for each oxygen? How many valence electrons? 6 for each, so that's 12 total, and 2 more hydrogens plus 2. So when we add these all up together, we get 10, 22, we get 24 electrons. And when we count them here, you get 8 here and 8 here for 16, plus another 8 here for 24 electrons. So this is a fine Lewis structure. So let's look at the carbon. The carbon has 4 pair. So what's the hybridization? sp3, and it's going to be tetrahedral. What about the boron? How many pair? 3 pair. So it's going to be sp2 hybrid, and it's going to be trigonal planar. What about both oxygens? So I'm going to write one oxygen down because they both are represented the same way. 4 pair, and it's going to be sp3 hybridized. The orbitals will be tetrahedral in orientation, but the molecular geometry is bent. And it's about 109.5. So we can actually draw this and kind of show all of that. So I'm going to start with my tetrahedral carbon. Going off to my boron, which is trigonal planar, going off to my oxygens, and my oxygens are bent. And so here, sp3 hybridized, here, sp2 hybridized, here, sp3, here, sp3, and this one is bent 109.5. This one is bent 109.5. This one is trigonal planar 120 degrees, and this one is going to be tetrahedral 109.5. Okay, so that's it for that problem. Now let's look at bonding in acetic acid. So using valence bond theory, describe bonding in acetic acid. So here we want to get the right Lewis structure. And we know with the CH3, it's going to look like this. So here with the CO2H, we want to do this. And it makes the most amount of sense to put the hydrogen on one of the oxygens, otherwise it's not going to work. And this is what the structure is going to end up looking like, a double bond to this one oxygen. So if we want to draw this, what is the hybridization here? sp3, and that's going to be tetrahedral, 109.5 degrees. And let's go ahead and draw that. And that goes to this carbon here. What's this? So that's this carbon. How about this carbon? Well, this carbon is going to be sp2 hybridized because it's got 3 pair. And so that means it's going to be trigonal planar. You can see I'm abbreviating things. and that's going to be 120 degrees. So here, it's going to look like this, and I'm going to draw this like that. And then this oxygen here is going to be sp3 hybridized, but it will be bent 109.5 degrees. And I'm going to draw it like that. So using valence bond theory, we just described what's going on, but we have a little bit more. And that's that this oxygen has 3 pair, so it's sp2 hybridized, and it's going to be trigonoplanar, 120 degrees. And so now we explained most of the bonding in here, but we need to also describe here that there is a pi bond here. So whenever you see a double bond, there's always going to be a pi bond. And in fact, you want to just memorize that. When you're looking at bonding, if you have a single bond, it's a sigma bond. If you have a double bond, one of them is going to be a sigma, one's going to be a pi. And if you have a triple bond, one's a sigma, and there's going to be 2 pi bonds. That's the way it is always with single, double, and triple. The first one is always a sigma. The second one is always a pi. The third one's always a pi. And this also explains why you don't really see 4 bonds between 2 atoms. It's because you can have 2 parallel p orbitals, the 2p y and the 2py and the 2pz and the 2pz. And so here's one pi bond, the pz's and the pz's. Here's one, the py's and the py's. The x's, they do this and they do a head-to-head overlap, which makes it a sigma bond. Okay, so that's bonding in acetic acid. So let's put that over there. The second half is going to be about molecular orbital theory. Let's take a little break. Thank you for listening.